This is the fifth in a series of resources on limits. We consider the basic idea of a limit and provide a formal mathematical definition for a limit. We look at three instances where a limit does not exist. We explore various properties that make finding limits simpler and look at multiple examples. We consider what it means for a function to be continuous as it pertains to limits. We close the series by considering infinite limits. In earlier resources, we learned that functions that grow without bound do not have defined limits at those values. This is true, but we also say that those limits equal infinity. Let's provide a formal definition for limits that are equal to positive infinity for some function f at a value c. Suppose we have any value m that is greater than 0. We can find a delta, also greater than 0, so that there will be an x value at most delta away from c where the function value is greater than m. So no matter how large of a value, we can find a function value that is larger. Functions may also have limits that approach negative infinity. The formal definition for this type of limit is very similar to its positive relative. For limits equal to negative infinity, suppose we have any value n less than 0. We can find a value delta greater than 0, where some x value less than delta away from c has a function value less than n. So no matter how massively negative a value, we can find a function value that is more negative. To summarize, consider a limit as x approaches some value c for some function f of x that is equal to positive infinity. This means that at c, the function grows without bound. We can extend this definition to include the ideas of approaching c from the left or from the right. If we look at a limit as x approaches c equal to negative infinity, this means that the function decreases or gets more negative without bound. Again, we can extend this definition to include the ideas of approaching c from the left or from the right. What do these infinite limits mean for the graph of a function? If a limit is equal to positive or negative infinity at some point c, we say that there is a vertical asymptote at c. But what exactly causes a vertical asymptote to form? In short, it is division by 0. The only exception is the case where we have 0 divided by 0. If we have some rational function h of x defined by the ratio of two functions f of x and g of x, then the graph of h of x will have a vertical asymptote at c if f of c does not equal 0, but g of c does equal 0. Let's look at an example. Suppose we want to find the asymptotes for the graph of the function f of x equal to 2x divided by the quantity x squared minus 9. To find the asymptotes, we set the function in the denominator equal to 0 and attempt to solve. We have x squared minus 9 equal to 0. We can factor this polynomial. We have the quantity x plus 3 multiplied by the quantity x minus 3 equal to 0. Splitting the factors gives us x plus 3 equal to 0, or x minus 3 equal to 0. Solving, we find that x equals negative 3, or x equals positive 3. However, we do have to ensure we do not have the indeterminate case of 0 divided by 0. Neither 2 multiplied by 3 or 2 multiplied by negative 3 equals 0. Therefore, the graph of 2x divided by the quantity x squared minus 9 will have vertical asymptotes at positive 3 and negative 3. Take a look at the graph. We see the main part of the graph with the vertical lines at x equals -3 and at x equal to 3 drawn in. On one side of each of these vertical asymptotes, the graph approaches positive infinity and negative infinity on the other side. But what happens to a graph as we approach infinity? In other words, what is the end behavior of the graph? For this limit as x approaches infinity or negative infinity to exist, the function must be some form of a rational function. We can think of our function h of x as the ratio of the functions f of x and g of x. Assuming that each of these functions are polynomials, the only terms that matter as x gets larger and larger are the leading terms, the terms with the highest exponents. Assume that the leading term for f of x, the function in the numerator, is a multiplied by x raised to the m power, and that the leading term for g of x, the function in the denominator, is b multiplied by x raised to the n power. We have three possibilities for the limit as x approaches infinity, and they depend on the comparison of m and n, the powers from the leading terms. If m is greater than n, or the numerator has a higher power than the denominator, then the limit does not exist. The function will grow without bound on the ends. If m is less than n, or the numerator has a lower power than the denominator, then the limit will be y equal to 0. The function will get closer and closer to the x-axis as we go further out in x. If m is equal to n, or the numerator and denominator have the same power, then the limit will equal a divided by b, or the ratio of the coefficients. As x gets large in either the positive or negative direction, the graph will approach the line y equals a divided by b. Let's look at some examples. Suppose we want to find the limit as x approaches infinity for the quantity 4x to the 7th minus 9x to the 4th plus 5x plus 2 divided by the quantity 2x to the 6th plus 7x squared minus 11. We focus on the leading terms for the numerator and denominator, or 4x to the 7th and 2x to the 6th. 7 is greater than 6. Because the power in the numerator is greater than that in the denominator, the limit as x approaches infinity is also infinity. Looking at the graph, note that the graph points up on the right and down on the left, so our guess about the end behavior was correct. What if we want to find the limit as x approaches infinity for the quantity 4x to the 5th plus 2x to the 3rd minus 7 divided by the quantity 2x to the 7th plus 6x squared plus 1. Focusing on the leading terms, we have 4x to the 5th over 2x raised to the 7th power. 5 is less than 7, so the limit is equal to 0. Looking at the graph, the ends of the graph move close to the x-axis. And if we want the limit as x approaches infinity of the quantity 4x to the 5th plus 9x to the 4th plus 2 divided by the quantity 2x to the 5th minus 4x to the 3rd minus 3, when we look at the leading terms, we have 4x to the 5th power over 2x to the 5th power. The powers match up and are equal. So the limit as x approaches infinity will equal the ratio of the coefficients, 4 divided by 2, or 2. When we look at the graph, as x moves farther out, the graph approaches the line y equals 2.